notice that we have editors for all these models. So you can edit script and use them.
No, I was just asking if they have infrared idea.
So this is what you can, like this is the multi-domain coupled here in the circuit simulation. Now you will have batteries. Battery simulation is possible. You can do the thermal analysis of battery. You can extract the thermal circuit from the battery. You can simulate the battery here completely. So every aspect is addressed, whatever you think of. And this is what is solution that we have. So if you look at this chart or a wheel sort of thing, this is what is simpler, is well coupled, and it can talk with all these tools. This simpler Simulink, Hardcat, model scene, and this is how it is well coupled with these tools. And there is like no need to assume anything in this area. We are assuming something, we are coming back. We are making some assumption that thermal stability is there, we are coming back. So this is the actual simulation. That is what is my title is. This is a simulation driven design. So that's all I have. If you have any queries, you can just mail me. And ANSYS is ANSYS is thankful for Rakesh sir giving this opportunity to interact with you and demonstrate. This is just an overview. If you need some details, definitely you can be in touch with me.
You can send us a copy of this.
Yes, Rakesh sir will send it. So thank you, sir.
Thank you, Ashish. That was very informative. Ashish is taking orders. Anybody wants to place an order for
But he didn't tell the price. He is not voting for it.
No.
Price is only told after you place an order.
No, I will send the appropriate people who can negotiate the price.
But you can negotiate the price. Okay.
Oh, wow.
Thank you. That was good. All right. So we give a simple 0.5 DutyCycle command, and then we basically expect it to linearly respond to this DutyCycle command. So here, that's about it. That's the whole circuit, right? And some of the parameters here we have is we are running V input is 12 volts, L is 100 microhenry, C is 10 microfarad, R is 10 ohm, that's a load, max duty of 0.99, and the minimum duty of 0.01, gate drive voltage of 5 volts. We don't have type 1 amplifier here, so you can ignore these parameters. You have this PWM running at about 100 kilohertz, right? So, and this is the waveform. You have overshoot at 9.5 volts, and then it kind of stabilizes at 6 volts. So DutyCycle of half, you have 12 volts. DutyCycle of half will give you 6 volts, right? This is the inductor current. As you can see, it also has an overshoot, and it stabilizes to about 6 volts, so about 0.6 amps. 6 volts divided by 10 ohms is what the resistance was. Now, what we do is use our magic switch. So exactly the same circuit, and we've taken the diode out and the switch out and replaced by this ACP block with a DutyCycle command. And now the PWM generator is gone, right? So we just give a direct 0.5 DutyCycle command, and here are the results. So we have a 9.6 volt peak, but there is some additional ringing. I don't know why that is, but anyhow, the end result is that it stabilizes to 6 volts, and this is the inductor current. So it goes to 2 amps and then stabilizes to 0.6 amps. And let's go ahead and fire up the PSpice circuit. Demonstration number 16. A little time to load up. All right. Open project. Okay. So we have the CycleByCycle. So here. So both of these can run at the same time. So you have two schematics here, CycleByCycle, and then you have also average switch here. Okay. So we're going to run them. Relatively quick, and we are going to, let's see, do new window, and here let's do CycleByCycle first. So let's look at the output. Let's look at the output voltage first. So we have the output voltage is of the grid. See it. So that's the output voltage. Okay. And then we can look at the inductor current. We add an axis to this. Then we add the inductor. So that's your inductor current. We can zoom in to see a little more detail. And we can also plot voltage across the inductor. Shows you voltage of the inductor, and we can go to like so every cycle the voltage has to go to 0. Average voltage has to go to 0. So you can see it has got positive and negative cycles. Average voltage. Okay, and then if we can also look at the voltage across the switch. This is here we can so let's say drain to source. So that's the voltage and then we can also see the voltage across the diode. And normally you want to know the diode current shape. So that's your diode current.
Can you see the diode voltage?
Yeah, yeah. Plot it on here. Okay.
So it does one negative. There is a diode drop there. Do you want to diode voltage?
Yeah.
Negative voltage.
Pardon me?
Go to steady state waveform.
Reverse state. So you have
What is the lowest voltage that you have here?
see the lowest voltage we have here on the diode. It is it's about 3.3.
Something wrong with the diode parameters.
Yeah.
Should be like 0.6 or 0.7.
Maybe that you want short key mode. Short keys.
Depends on the diode model.
Yeah, yeah. I think we can actually bring in a diode. This would be a good one to do.
That's okay, just curious. I'm sure it'll go in. The correct diode is used. The parameters may not be correct.
Okay. Yeah, I think you can definitely replace the diode and see the results. That may be one reason why we have some difference in the average switching in the cycle by cycle. Now, we have, let's look at the average. So here, so let's do a new window. So we look at the output voltage. That's your output voltage, and then if you look at the current, that's it. Okay. So there's no switching in this model, and you're able to essentially get a basic circuit behavior. Then how is your circuit behaving?
So here, if you see that voltage across the inductor, it will just be 0.
Yeah. So let's do that. So if you see the voltage across the inductor, it should be 0. So this, and it basically goes to 0.
Inductor current will be rising.
Steady state voltage across the inductor is 0. You have voltage swing here, which goes from 6 to -4, but eventually when you reach steady state, it goes to 0. Okay, and let's see here. So this is the buck, and let's go to any other questions on this one?
Can you show us how we do the body plot?
Oh, you want to get to that?
Just
Okay.
only for one of the demos.
The body plot, let me actually, we're going to get to the demonstration. I can actually do it. Okay. So what we do in a body plot, so this is your average buck, okay? And here, since we are going to stability analysis, so we have got a buck converter with parasitics, okay? We have parasitics here. We have added an inductor, a resistance and series resistance, and then series resistance for the capacitor and the inductor, right? And what we have here is an AC voltage source. Now this is your, let me zoom up. So this is your type 3 amplifier. We'll talk about these amplifiers in a few minutes, but this is a type 3 amplifier. Okay, now what you do is, in this type 3 amplifier, we inject, at this point of time right here, we inject AC voltage source. Okay, there's no DC component, the AC voltage source, right? And then what we plot, and then when you are trying to determine the open loop transfer function, okay, you're going to plot V out, okay, V out 1 divided by V in. So that will give us the plot for the power stage, right? It'll give the plot for the power stage. And you can also plot EA out by V in, which will give you the plot for, V out 2 by V in. V out 2 by V in. So you can plot V out 1, which is same as this, right? By V in, it will give you the Bode plot for the power stage, right? And then if you do V out 2 by V in, it will give you the Bode plot for the whole power stage plus the compensator. That's the open loop transfer function, right? So the part you're trying to do, you say, okay, my power stage Bode plot is like this, and it seems too close, and it may not be stable because either the phase margin is not there or the gain margin is not there. So compensator, we try to adjust the phase margin, and you want to make sure that once you have set the phase margin correctly, then you run the Bode plot again for V out by V in, and you kind of get an idea of, okay, we are in pretty good shape at up to the crossover frequency, right? So if I run this simulation, okay, that's basically a second order system, right? You have an LC and R system here, so that's what it shows. So this is the power state. Now if you want to plot the body plot, what you do is, let's do a new window, and we're going to say trace add. We're going to go here and go to plot window template. We're going to pick up, let's say body plot separate, okay? And we're going to pick up voltage here, V out 1. I can just type it. Okay, here's V out 1. So because my V in is 1 volt, I don't have to really divide it by V in, right? This is just 1. So I can just plot V out. So when you plot this, so here it is on the top, you essentially have, this is your phase plot, and this is your gain plot, right? And this is your gain plot for power stage. Okay. Now here, if I go to 5 kilohertz, okay, let's see if I want to go to. Now, what I normally like to do is actually 20 times log